All right, let's get started with these notes for topic 1.4. So this is basically our remembering about polynomial functions, different properties of polynomials. All right, so the math explanation or the math format of a polynomial function is this right here. So remember, a polynomial is something like this. I mean, that's all that this is saying. This an minus 1, an minus 2, those are the coefficients of the terms, all right? And so the leading coefficient is a to n, a sub n, and then the degree is your n right there. Now remember, your degree has to be a whole number. Right? It can't be a negative exponent. You can't have fractions or decimals up there. You have to have a whole number. And, you know, if this is 5, then that's 4, 3, 2, and so forth, like that. And so the leading term is the thing with the highest degree, right? So an x to the n. So that's just like the math for what a polynomial really is. All right, and these rules here. There. All right, so we're going to find the leading coefficient and the degree of each of these things. So the leading coefficient is 3, because it's the number in the coefficient in front of the x to the 4th. It's the one with the highest power. The degree is 4. Okay. My leading coefficient is really supposed to be this guy right here, if it was in standard form. So -7, my leading term actually, and the degree is 3. This one, there's only one spot. This is called a constant function because there's no change. There's no x in there to change the answers. It's constantly 4. So the leading coefficient is 4. The degree is 0 because really, technically, you could write 4x to the 0 is what you could say. And then x to the 0 is 1, right? All right, so the extrema. Extrema are like extremes. It's just like a fancy math word for the maximums and the minimums. The extrema of a graph are the minimums and maximums of a function. There are two types of extrema, relative and absolute, also called local extrema or global extrema. So, you know, the whole world or just local to your area, okay? So, looking at this picture right here, now notice it stops right there, and then this one has an arrow. So that arrow means it keeps going down. So this graph is not going to have an absolute minimum because it goes down forever, but it does have some local ones. All right, so there's a local minimum, like a low spot right here, any kind of dip, and that's it. X equals 0. Now, you might also think this is a local minimum. An endpoint cannot be a local minimum because to be local, you have to have stuff around you. You have to have something to the left and to the right of you. So no endpoints can be counted as local, but they can be counted as absolute maximums or minimums. So for instance, well, let's take a look at this one. Local maximums, so here and here, so at 2 and at 3. Now just to point out, at 3, that's actually an absolute maximum because it's the highest on the whole picture. But all right, absolute maximum. So this is the absolute tallest. The maximum value is 2, and it happens at x equals 3. An absolute minimum. All right, so where is the lowest on the whole graph? This graph right here. Just checking something. This graph right here doesn't have one. There's no such thing. Since this keeps going down forever, if this stopped, I could say that's an absolute minimum, but you know, this graph just keeps going, going, going. So it doesn't have one. All right, on to the next one. So we got this picture. You notice it just keeps going. It just has it has a maximum. That is a relative maximum and an absolute maximum. It's going to have no minimum, no absolute minimum, because it just goes down forever. Okay, so relative minimum, there aren't any. Relative maximum happens at x equals 1. Right here. All right, absolute minimum. There aren't any because this graph goes down forever. Absolute maximum, this is also the highest on the whole graph, so it is a value of 3, happens at x equals 1. Okay. All right, over here, so endpoint there, goes down forever. So in looking at this graph, this looks like to be the highest point of the graph. this looks like the lowest, but this is just a relative minimum because this graph goes down forever, so it bypasses that. All right, relative minimum is going to be here at x equals -2. A relative maximum, let's see, this guy right there at 3. Now you might think, oh, this is a relative maximum, but no, because number one, it's an endpoint. Endpoints can't be relative because they don't have something on the other side. And yeah, it can't be relative. So absolute minimum. So is there absolutely a lowest place on the whole graph? No, it goes down forever, so nothing. Absolute maximum, right there. So it is a value of 2. It happens at 3. Okay. All right. This picture, oh, 2 endpoints. Okay, so I noticed that this is the highest on the whole graph. So that is an absolute maximum. An endpoint can be an absolute maximum, but he is not a relative maximum. Here's a relative maximum. Here are relative minimums. Now this relative minimum is also an absolute minimum because he's the lowest on the whole picture. This guy, he's just nothing. He's just like in the middle somewhere. All right, so relative minimums happen at -3 and at +3. Relative maximums happen at 0. Absolute minimum happens at -3, and the answer is -3 also. Absolute maximum happens here. The answer is 4, and it happens when x is 5. Okay, so some things about polynomials. Between two real zeros of a polynomial, there must be at least one local maximum or local minimum. Remember, local is the same as relative. So think about what that's saying. If I draw a little picture, if you have two real zeros and you're trying to travel between those, well, if you're going to travel between them, you either have to, like, you know, maybe go up through here and back down. So, oh, there's a maximum, or maybe you came down and went through, there was a minimum. Okay, you can't just go straight across because there's nothing to make that happen. All right, so polynomials of an even degree. So remember, even when you have x to an even power, both ends go down. If it has a negative in front of it, both ends go up. So if everything's going down, then you can have an absolute maximum. If everything's going up, you're going to have an absolute minimum somewhere. But when you have a graph like this, like if it goes opposite ways, you'll never have an absolute max or min because the graph always goes down forever and up forever. Okay, so when you have an even degree, they are going to have an absolute maximum or an absolute minimum, depending on their leading coefficient. All right, wrapping it up here. Okay, so points of inflection. So when you have points of inflection, you know that a point of inflection occurs when the graph changes from concave up to concave down. And it kind of happens like in the middle of your max and mins. Like look there, here's a minimum spot, here's a maximum spot. So the point of inflection, unless I'm told differently, I'm going to kind of assume it's like right there. That's my point of inflection. Okay, and then over here, you know, there is a minimum spot, and so probably the point of inflection is right here. Unless somebody tells me, I'm just going to kind of assume that's where it is. That's all I can do. All right, a point of inflection. At a point of inflection, the rate of change of a function changes from increasing to decreasing. Remember, if you're concave up, your slopes, your tangent line slopes are increasing slopes. If you're concave down, they are decreasing. All right, and then concave up, increasing again. And the point of inflection is where you change, your rate of change changes from increasing to decreasing or vice versa. All right, the graph is shown above. Use the graph to answer the following. So find any values of x where there is a point of inflection. So I think it is at x equals -1 and +1. All right, for each of the following intervals, determine if the rate of change is increasing or decreasing, and explain your reasoning. All right, from 3 to 4. So from 3 to 4, this area here, I am on a concave up area, so my rate of change is increasing because what's the name of this guy? G of x is concave up. Okay. From -4 to -3. -4 to -3, another concave up part. So same. Okay, kind of lazy, but let's see, -1 to 1. That is part of a concave down area. So my rate of change is decreasing because g of x is concave down on that interval. All right, and 1 to 2. 1 to 2, oh, that's a concave up part. So the rate of change is increasing because g of x is concave up. All right, last part. Okay, so we need our calculator. So from, let's see, 0 to 3. So I'm going to go ahead and draw this graph from 0 to 3. 0, oh, I don't know. Oops, I didn't mean to make that dot there. So 0 to 3. All right, oops, whatever. Okay, I got a function here, 5th power. That means there could be 4 turns. So look what I know about this problem to begin with. X to the 5th power. So I know that it's odd, so the right side goes up and the left side goes down, but that switches because of the negative. So left side goes up, right side goes down. And I know I could see 4 turns. Okay, I don't really know the x-intercepts because this is like so messy and hard to factor, but let's go ahead and put in our calculator. All right, so let's see. Oh, let me turn that plot off. All right, so we got -1.37 x to the 5th plus 4.218 x to the 4th. All right, gotta use x's instead of t's. Minus, make sure you're using this minus sign, not the one down below, because that's a negative sign. 0.357 x squared plus 3. All right, now I'm just going to do zoom 6. Zoom 6 is my normal picture, and then I'll fix it up. All right, so first of all, they only want me looking from 0 to 3. So my window, so I'm going to do 0 to 3, but I'm also going to want to see higher than I'm seeing now. So my window, I'm going to do 0 to 3, and the scale is 1 is fine. I don't really need to see that low because the graph wasn't down there, but I do want to see higher. So let's try like 25. So that way I see a little bit and make sure there's nothing there. Oh no, I need to see higher. So let me change my height. Let's do like 40. Let's see if that's high enough. All right, now remember, 0 to 3 is all I'm looking at. I know this graph keeps going here and it keeps going over there, but this is all I care about. So I'm going to copy that on here. So it looks like it's kind of like that. All right, so let me do this. 3 is where I'm stopping. So let me do trace and then type in 3. So 3 and 8.535. And let me also do 0, 0, 3. I also knew that because of that. Okay, and let's go ahead and find this maximum spot right here. Okay, so second calc, maximum number 4. Now look, this maximum, it's between 2 and 3. So instead of using this little blinker, I could just literally type in 2, and it starts, and then type in 3. And then it's going to look in there. I don't have to like do all the little moving across, so then don't want to guess. All right, so there's my maximum at 2.446, comma 31.898. All right, so these are the important things on my graph. Okay, all right, so based on this model, at what time does the number of cars in the parking lot change from increasing to decreasing? Okay, so I want to know when the graph changes from going up to going down, and they're asking me for the time. So remember, this is actually my time right here. So it happens right here, increasing to decreasing. So at t equals 2.446, that's a 4. And what is this, seconds or something? Hours. There we go. All right, and so this was your homework to get this done, and I'll see you in class. Bye-bye.